Hello สวัสดีครับ we are going to have one more extra example on statically determinate beam. We are going to do two things for this. One is we are going to draw the influence line diagram for the reaction, for the shear force, and for the moment. And then when we do this, we're going to use the proper scaling to make the influence line looks beautiful and nice. And we also going to determine the second thing is the loading pattern. Okay, and by doing this, we have the uniformly distributed load of 100 kilonewton per meter and the concentrated live load of 500 kilonewton. And by this loading pattern, we're going to determine the maximum reaction and also the maximum moment. This is reaction at A and the moment at F. Okay, let's just consider our beam. This beam is statically determinate beam. You guys are now be able to check it already, right? And by considering this beam, the beam gonna be rigid beam. That means when we draw it, all the moving shape, moving and rotating, going to be in the straight line. And what we have is the beam here. Okay, very long one. And let's just project it a little bit so we can draw it beautifully later. Just project the line along each point A, B, C, and this is B. Okay, and let me start. We're going to use the Muller's base law principle to draw the influence line of this beam, and let you record it. If you like to draw the influence line of the reaction, what should you do? You should start by considering the beam at that point A, and then you release this. Release what? Release A sub y. So that means for this beam, you have the A sub x and A sub y. When you release only A sub y, there's still the reaction A sub x. So this pin change to this roller. Okay, and then the pin is still there, and the roller, and the roller. And then if you like to make the movement of the beam, we got to push the beam with the force reaction of A sub y, and then you move that point for 1 unit. When you move that point for 1 unit, that 1 unit is 1 centimeter. Okay, you will get this one. And what happened is, since this beam has the hinge here, and this portion of C, D, E, F, G has two roller connection, and the beam is a rigid beam. This means this portion would move, and then the rotating point going to be here. And since the rotating point is being here, and then you push by the A sub y for 1 unit, so it's going to change the shape like this. Okay, and you arrive the influence line diagram of A sub y look like this. Okay, next, let us draw the influence line of the shear force at D on the right side. So D is here, D is here. Okay, it still have the roller support here, and the F also have the roller support here, and we have the hinge here, we have the pin here. What happened is you got to eliminate the resistance to the shear at point D on the right. That means you got to put the roller guide on the right of point D. Okay, and then you got to push this portion by the positive V sub D downward on the left hand side and upward for the right hand side. That follow the sign convention that we have since the engine static. On this one, we're going to have the moment like this as a positive, and then we have the shear downwards on the left and upward on the right to be the positive shear, and this is sign function for positive moment. And what happened is, since this one has roller guide, so when it's subjected to the force, this portion, this end will move, and this one is rotating point, so the movement is going to be like this. How much is going to move? It's going to move with respect to this point, and since this point going to move downward, but is very small cut from the point D, so there is no movement here. Since there is no movement here, this one gonna be freely moved for 1 unit, so it's moved to here, and with this one as the rotating point, so the movement gonna rotate in the form like this. Okay, and then you have this with what 1.0 here. Okay, and since this one has no movement, but the rotation that is going to have is going to be in parallel to this. So what we have is you extend this one, and the 1 unit is the relative displacement here. And since this is 1 divided by 6, and this also 1 divided by 6, so this is 6 meter, this is 6 meter. So by similar triangle, you get this is 1.0. And then since this one can rotate, you can connect the point to be like this. That's going to be the inference line of V sub dr. Oh, also, since this one is 1 divided by 6, this also 6 meters, so this one going to be minus 1.0 here. Okay, and the last one for this, we're going to draw the inference line diagram of M sub F, and what we have is this is going to be the pin, the same as before, the hinge, the roller, okay, and then this is point F. You like to draw the inference line of M sub F. You're going to eliminate, okay, the resistance to M sub F by putting the hinge here, and then you apply the M sub F to make the beam move, and what you have is this portion of C, D, E, and F have to support. When it has to support, no rotation be able to move, right? There is no rotation or movement, so only this side gonna rotate by 1 unit. And since this one is 6 meter, so this one also gonna be for 6 meter, and then you get the shape of the inference line of M sub F like this. And also this is 1.0 unit, and this is 6 meter, so this one going to be minus 6. Okay, and now we're going to put the uniformly distributed live load. That is going to be LLW equal to 150 kilonewton per meter. And you also have LL concentrated load. That is going to be F. It's going to be 500 kilonewton. And when you put this live load and you're going to find the loading pattern, you got to consider the area. Okay, this inference line of A sub y has the positive area. So that means the uniformly distributed like load gonna cover all this, okay, all this area, and it won't go over here because there is no point to be here. There is no influence here, and then the point load gonna be at the highest coordinate at that influence line. So the point load gonna be here, okay. That's going to be the loading pattern for produce maximum A sub y. And next, let us put for this one, okay. And you may have this always have negative effect. So the uniformly distributed live load gonna cover this area. And since this is the maximum coordinate of the influence line, so we have the concentrated live load 500 kilonewton here. So that's supposed to be the loading pattern to produce maximum A sub y. This is going to be the loading pattern that's produce maximum M sub f. Okay. If you can understand that, we come down to draw the pictures for that. And for this one, let us just copy it. That is going to be in between this point and that point. Just put this 150 kilonewton per meter here, and we have the pin and hinge here, and roller here, and roller here, and one more. The point gonna be at the highest coordinate, and then put this one here, okay. And what we have, we are determining the A sub y. The A sub y gonna be what? The A sub y gonna be 500. A sub y going to be 500 times 1. This 500 gonna time this coordinate 1. And 150 gonna time the area here. Okay, so we have 500 kilonewton, and it's gonna time 1. Gonna time 1 here. Let's put this 1, and then you have 150 kilonewton per meter plus 150 kilonewton per meter, and it's gonna time this area. It's gonna time 1/2. That is 12 meter. Okay, time 12, and then time 1. So what you get, this is gonna be 500. Okay, and this is 6. This is gonna be 600, right? No, 900. Okay, it's gonna be equal to 500, and then plus 900. That is gonna be what? 1,400 kilonewton for this one. Okay. And next for this one, we just put this one as the pin, hinge, roller, and roller, and then we put the uniformly distributed load 150 kilonewton per meter here, and the point load of 500 kilonewton. So you have here is the M sub f. Okay, M sub f. M sub f now is going to be what? Equal to what? Equal to 500, right? That's 500. 500 is going to have what? 500 is going to have -6. That's quite a lot. 500 kilonewton times -6. And you also have this is plus 150 kilonewton per meter, and that's gonna time the area here. That is gonna be 1/2 of 6 meter and time minus 6. Okay, that's going to be quite a lot. This is gonna be like minus 3,000, and this one cut's gonna be 3, and this is minus 2,700, and finally we get this for 5,700 kilonewton meter. Okay, that's is for the m sub f. This is for the a sub y, and then you may put this one. The a sub y is 1,400 kilonewton, actually upward. Okay, this is going to be 5,700 kilonewton meter, and it's going to be negative. Don't forget to put negative over here also. Negative kilonewton meter is in the opposite direction of here. Okay. Okay, we did a very nice job, and actually we still have author influence line diagram to work on. If you like, if you like, we just expand this. This is about, just make it of 1.5, 3, 6, 7.5. Let's put it 7.5. This is going to be 6 meter, 6 meter, 6 meter, and 6 meter and 6 meter. Okay, if you put this one to be like okay, 9 millimeter here. That is going to be the starting point, and then you may put this one 1.5, 1.5, 1.5, 1.5, and another 1.5. Then you may draw this one clearly. Okay, to make space for us to do some more practice on the influence line diagram. So which one you like first? I recommend to start by the reaction. Okay, let's start by the reaction. And this one gonna be point A, and this one gonna be the pin, and this is B, this is gonna be C, it's hinge, and this is D, and this is F. Okay, and this way G. And then you have the influence line of A sub y already. Let me have the influence line of D sub y. Okay, if you like to draw the influence line of D sub y, you eliminate the resistance to the D sub y and put the D sub y there to move it for 1 unit. You move it for 1 unit. Okay, you move it for +1. And what happened is, when you move this one, this is going to be the rotating point. This one, rotating point. And then when it's moved, it's going to move like this, 1 unit. Okay, and by the rigid body movement or rigid beam movement, you will get the shape of this portion like this. And then you have this one as a rotating point. This one has rotating point, and then you push it up. Okay, you push it up, push up, push up, push up. It's going to be like this. And then you draw the shape of this, and this one is up to this point, and you have this. Okay, this is going to be the influence line of D sub y. And then what? This one, you just connect this one to this one. And since this one is 1 divided by 6 meter, and this one also 6 meter, so this one gonna be -1. And again, this y divided by 12, and this one divided by 6, so this is gonna be +2, and this is going to be inference line of d sub y. And then we have the f. Okay, the f here, we have the f here, we do the same. F is here, a the same, and c hinge, and d the same. You what? You eliminate the resistance to f sub y out, and then put the force f sub y to move this thing up for 1 unit. Okay, this move for 1 unit. And again, when you move like this for 1 unit, this is the rotating point. This one gonna move up like this, and you get this line. Okay, it's going to be in the linear, and this one going to be downward, and this is 1 unit. This is 1 divided by 6 meter. This is 6 meter, so this one going to be -1. And again, this one is 6 meter. This one divided by 6. This one y divided by 12. So this one going to be +2. Okay, and you have this connection to finish the inference line diagram of f sub y. This is inference line of f sub y. Okay, and then let me move to a df onก่อน. Let me move to consider the shear, right? The shear. Let me consider shear, and we have the shear at the d on the right. Let me put the shear force at d on the left. Okay, this one is like this. This hinge, C still here, and F still here. We like to draw the inference line of V sub D and L. That means we consider the left is here, okay, and put the roller guide along this. Then we need to put the downward shear. It's going to be plus V sub D L, and this one going to be up, okay. And then this has the 2 roller support here. You're trying to move here. That is they are going to resisting your force. So this one won't move. It's going to be rigid beam here. That's going to be rigid beam here won't move. And since this one won't move, the condition is this guy must move with the parallel with this, and the movement here going to be -1.0 downward. And then you got the hinge here, you connect everything together, and then you got the inference line of V sub DL. Okay, next, let us consider the inference line of V sub B. Okay, V sub B. Let's see inference line of V sub B. We have this, okay, before also this one, okay, and the hinge here and the pin here. V sub B, that means the B is going to be here. What you do is release the or eliminate the resistance of V sub B, and then you move downward on the left, you move upward on the right, and you have A equal to 6 and B equal to 6 and the L of 12. Okay, and this one gonna move downwards like this, and this one also going to move upward like this, and they're gonna be in parallel with the maximum of oh sorry I'm sorry on that, I didn't check this. It's with the maximum of relative displacement of 1. Okay, and that's going to be the inference line of V sub B. Okay, and then we have an inference line of M sub B. here, and then this is going to be the same. This is going to be the hinge, the support, roller support here, roller support here, because you're going to draw the influence line of M sub B. You release the resistance to M sub B. Put the hinge here and put the M sub B positive. Okay, and what happened is this point gonna move to somewhere here with the AB over L, and that is going to be what? This is 6 times 6 divided by 12, and you get it for 3. Okay, and then let's move here for 3, and this portion has the roller and roller, so it cannot move by the same lesson as before, and this one gonna move up and here, and we have the 1.0 relative angle here. Okay, that is going to be kind of easy, right? Okay, and then if you like, you may move to draw the influence line of M sub D. D here, this is D. Okay, influence line of M sub D. Okay, this is the D. You're going to draw the influence line of M sub D. D is here. This is F. This is hinge. This is the pin. Okay, what you do? Eliminate the resistance by putting the hinge at D, and then you put what? You put the M moment, positive moment, positive M sub D, and this one has 2 side support, no movement. When this one more movement, there's supposed to be 1.0 unit here, and then the shape here gonna be like this. Okay, and what you have, just connect the point here, and since this one is 6 meter, this one 1 unit minus 6. Okay, not that hard. And the last one, let us draw the influence line of M sub E. Okay, M sub E. M sub E. Put this over here. Okay, M sub E. E is here. E is here. This is going to be the pin. This is going to be hinge. The C close to here, and the F is here. You eliminate influence line of M sub E, right? You eliminate the resistance to M sub E, and then you put the positive moment M sub E to drive this one up. Okay, with what? With the AB over L. So this one is A, this one is B. It's going to be 3 times 3 divided by the total of 6. Okay, and then you got this for 1.5. And what we have is this part gonna rotate like this. Okay, and also this part gonna rotate like this. Okay, and the angle here is 1.0 unit. What is the coordinate here and here? It's not that hard. Just use the similar triangle. You will get it. This is what? 1.5 divided by 3. And this is y. This is 6. So this is going to be minus 3. And this is also minus 3. This is influence line of M sub E. Okay. See, it's really easy to draw the influence line diagram. It's also fun also. If you like, you may find a lot of beam in your textbook, and you should practice to draw the influence line by yourself. As an assignment, I would like you to use this live load, the uniformly distributed live load and concentrated live load, to put into your influence line and trying to determine the maximum D sub y, maximum F sub y, maximum shear, maximum moment. Okay, that is the end of this demonstration to solve the problem of inference line diagram of statically determinate beam. Okay, bye bye.